And the condition is this for concavity. F of v, let me just write f of v, but we understand this v is a 1 by n row vector. F of v is less than or equal to f of u plus the summation of all the partial derivatives, f sub j, that's the jth partial derivative, evaluated at u, times vj minus uj. Okay. From j equals 1 to n. Okay. So now what you're doing, see, in the simplest case, we just had one derivative. Now you have n partial derivatives, and each are multiplied by a vj minus uj. Okay. Where v sub j is just the jth term in that 1 by n row vector. And uj is the same thing. Okay. All right. So this is the condition you would have to show in order to show that f is concave. And just as before, the condition for convexity, you just reverse it. If this was, we change this to convex, then you just reverse the sign, not the sign, or the direction of that inequality. Okay. And again, strictly concave, strictly convex, you just look at the strong versus the weak inequalities. So if I made this, if I erased that, then this would be strictly convex. Okay. In the other case, this case here would be strictly concave. Okay. Now recall, suppose we have a function we know is strictly concave. Suppose you've established that this holds. Okay. Then how are you going to find, what are your first order conditions? Your first order conditions are find the critical value of u where all these partial derivatives are 0. So in that case, this would vanish. And you would just be left with f of v is always less than f of u. F of u would be your global maximum. Because the first order condition is that the partial derivatives evaluated the critical value of x, let's say it's u, are 0. Okay. So again, we get this idea of a global maximum or a global minimum. Okay. Well, it turns out there is still another method of establishing concavity and convexity. And in many cases, of course, this is the one I go over last. In many cases, this is going to be the easiest to use. And it involves the second derivatives. Okay. And this is condition 1125 on page 326. And I'll just read it because it's in the book on page 326. A twice continuously differentiable function, z equals, I'll write this part. We're dealing with this case right here. Z is a function of x1, x2, ... xn. Okay. And let's assume this function is differentiable everywhere, twice differentiable everywhere. So all the second derivatives exist. Then this function is concave if and only if this is concave. if and only if IFF, this holds. The second order total differential is everywhere negative semi-definite. What that means is this thing is always greater than or equal to 0. Everywhere. Okay. Then let's read the next part. The said function is strictly concave if the second order total differential is everywhere negative definite. So you could say Z is strictly concave and this is usually what you use. But actually, it's not an if or only if here, it's just an if. This is strictly concave if this second order total differential is everywhere negative definite. The second order total differential is negative everywhere. Okay. Okay. Let me illustrate this this case. Let me just take a simple example to illustrate this. And I'll actually follow the book because they start off with kind of an interesting example. Suppose you have this function. Z equals minus x raised to the fourth power. The first order total differential, you recall, see, Z is just a function of a single variable here, x, so this is going to be easy. Z is just a function of x, a single variable. So dz, the first order total differential, is just f prime of x dx. Okay. If you just have one variable, the total differential dz is just the derivative times dx. Okay, if you divide both sides by dx, notice you get dz dx equals f prime of x. Okay. So what is the second order total differential here? In general, given this, what is the second total differential going to be? Okay, no. We're just doing the general case first. Then we'll go back to this. So it's just this. You take the derivative of this with respect to x, so that'll be f double prime of x. Multiply it times dx times the dx that's already there, and you get this. Zach, that may have been what you were answering for this case where z equals minus x to the fourth. But more generally, it's this. Now let's substitute in. What is our first derivative and second derivative here? F prime of x is what? Okay. And the second derivative? Okay. So our second order total differential is just this. I think this is what you were saying earlier, Zach. Minus 12x squared dx squared. Now it's clear by just looking at this. Notice x squared, let's assume x is not 0. Then this term here is always going to be negative. Now maybe x is 0, in which case this is 0. But in any case, it's obvious, just looking at this, this is always less than or equal to 0. For x equals 0, it'll be 0. For any other value of x, it's going to be negative. So you would say, in this case, we know this function is convex because the second order total differential is everywhere negative semi-definite. Okay. Had we been able to show that this second order total differential was negative everywhere, then we would have been able to conclude that it's strictly concave. Okay. It actually turns out that in this case you could show that the function is actually strictly concave. But you can't show it by this because this is not everywhere negative. Okay. But you could have concluded that it's, at least it's concave using this. Okay. All right. This is a sufficient condition, but it's not necessary. Okay. Because here's an example right here. If you just graph this, you could see this is strictly concave. But our theorem just is enough to show that it's concave, but not strictly concave. Okay. So we have three different methods. Now, we have the algebraic method of determining concavity and convexity. We have the method using the first derivative. And we have methods using the second order total differential, whether that's negative definite or positive definite. Okay. And realize there is a difference. If you're looking at the second order total differential, whether it's negative definite or positive definite, notice it's for concavity and convexity, it has to be negative definite everywhere, not just at the critical point. Before, we were looking at the sign of the second order total differential at the critical point. But now, for concavity and convexity, it has to be negative definite or positive definite everywhere, not just at the critical value. That's the difference. Okay. Okay. Let's take a short break. And what I would like you to do is look at problem 2 on page 341. See, that's an example where you have a two-product firm. And see if you could figure out the answer to that optimization problem. And see if you could figure out whether or not you have a global maximum there or not. In other words, see if you can determine whether your objective function is strictly concave or not. Okay. So take a few minutes to work on that problem. And that's a problem that we'll do after the break.
Professor, does this class go for 2.5 hours still?
That's my understanding. Yeah. I'll check with Gene, but my understanding was that it would be 4 more sessions.
I think my schedule, based on online, it said 3:15.
For Monday, Wednesday. But this is for the Friday.
Okay. That makes sense. If there
Yeah.
were
It-
hour and 15 classes, that would be 12 weeks worth of
Right.
class time.
Yeah, so we only do this. We meet for like 5 Fridays, so it'll be 2.5 hours.
All right.
Okay. So do you all have your book with you? I can write the problem down if you don't have your book. It's all right for you to talk to each other. Okay. 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 No, okay. No. Yes.
Is this still with this?
Yes.
Yeah. It says from 2 to 3:15. Once we meet in Brian.
Okay.
And that's why everyone's confused.
Oh, okay. I think there is a mistake on the course syllabus.
Yeah.
Alan was saying, I said Friday from 2 to 3:15. We really should meet for 2.5 hours. But I'll double check on that. Thank you, Alan. I apologize for that. The most difficult part of this problem is figuring out what the objective function is. I'll give you a few more minutes to work on that. See if you can express profit as a function of Q1 and Q2. You could do it the other way. You could get, alternatively, you could get profit expressed as a function of P1 and P2. See if you can do it this way. Oh, this is not very good. That's better. Will, who are the Rebels? Is that the Ole Miss? Oh, that's right. Okay. Is that a baseball shirt? Did Ole Miss, did they win the collegiate baseball tournament in the NCAA? But last year or the year before, weren't they close?
Last year we went to the College World Series.
Right.
Virginia knocked us out.
Okay, so they,
both times.
okay.
Yeah, agreed. But we weren't as good this year.
Yeah.
So,
Yeah. All right, let me just see if you've gotten the profit function. We want to get it in this form here. It's a little tricky though. Profit is going to be revenue minus cost. So cost is already expressed as a function of Q1 and Q2. Now the trick is getting rid of P1 and P2. How do you do that? But notice it's a little bit more complicated than the problems we did before. Because notice Q1 is a function of P1 and P2. If Q1 had been function just of P1, you could have easily solved for P1 as a function of P2. But what can you do? Has anybody figured this out? What can you do in this case to solve for, to get rid of P1 and P2? In terms of Q1 and Q2.
I haven't done it with just an idea, but if we put P1 and P2 on the left for each equation, and then we could do the total differential or something.
Okay, your answer is half right. The first part is right. Let's just get P1 and P2 over on the left-hand side and rewrite this first equation as 2P1 plus P2 equals 40 minus Q1. And do something similar to the second equation. Rewrite the